Part 1, Thermochemistry. The topics for today: nature and types of energy, system and surroundings, heat, temperature, and work, calculating internal energy, symbol is U for that, and work, and enthalpy, which is symbol capital H. First of all, energy is the capacity to do work. We all know when we have plenty of energy, we can do a lot of things, and we all know what it's like not to have much energy. Energy is something that is very hard to measure because it just won't stay put, unlike mass. Most of the time we're interested in changes in energy versus how much energy something really has. Various types of energy. Potential energy, which is an object's position. Here it's more of a physics definition where we think of like maybe a car on the top of a hill. We know that if the brakes give out, the car comes flying down the hill. It have an awful lot of energy. Its potential energy is converted to kinetic energy when it does that, and then that car will do a lot of damage if it strikes something. So technically, all objects, all materials have some potential and some kinetic energy. Now, how much they have of each depends on the object itself, the bonds within it, the type of atoms involved, and the phase that it's in. Now we have other types of energy besides these two major types. We have what we call radiant energy, which is energy from the sun. Thermal energy, which is heat energy, and that's due to the random motion of atoms and molecules. Chemical energy, which is what we're really concerned with here, and that's the energy that's stored within the bonds. We have nuclear energy, energy stored within the nucleus, and we're interested in that when we talk about atomic bombs on nuclear power plants. So how does an atom or molecule possess energy anyway? Well, here's a nice chart that shows you some of the different types of kinetic and potential energy. So on the left, we have a chart showing you various types of kinetic energies that a molecule will possess. So here we have translational energy, which means a molecule moving from one place to another. Here we have rotational energies, meaning a molecule can be thought to spin on its own axis. Vibrational energy, and it's shown with these springs here. We think of bonds more like springs rather than nails holding atoms rigidly in place. Atoms can vibrate in place. If you think of these atoms vibrating, they'll vibrate with a certain frequency. And then we also have electrons spinning around the nuclei of atoms. So these are the various types of kinetic energies. Now over here we have potential energies. Here we have vibrational as well. So you notice vibrational energy is both potential and kinetic. As atoms move further away from each other, their attraction increases and they start to be drawn towards each other. So they can vibrate this way as well as vibrate in this direction. We also have the attraction for the nucleus for electrons. We have the attraction for the protons and the neutrons for each other, binding the nucleus together. And down here we have our bond energy, which is what we're really, again, more concerned with. And that bond energy is really the attraction for the two nuclei for these shared electrons. Now, no one can really calculate these various types of energy by themselves. All we really care about is the difference in energy when a reaction happens. Energy changes in chemical reactions. First of all, we want to be able to talk about is the difference between heat and temperature. So heat is a transfer of thermal energy from one object to another, whereas temperature is not a measure of heat. Temperature just tells us which way the heat's going to flow. And heat always flows from where the temperature is higher to where it's lower. So which of these two objects has the greater thermal energy, meaning which one will release the most energy when they change temperature? So let's say we start off with the air temperature being 25 degrees, and we have a hot cup of coffee at 90 degrees centigrade versus a bathtub full of water at 40 degrees. Now both of these samples of water are going to lose heat to the air, and that's because the air is cooler. So heat always flows from where the temperature is higher to where the temperature is lower. So both the coffee and the water in the bathtub will cool down and eventually become the same as the air temperature, 25 degrees. But which one of these two objects will release more heat? Well, you might think that it's the hot coffee because the temperature is much higher than it is for the water in the bathtub. But because there's so much more water in the bathtub, the bathtub is going to release more energy to the air. So that bathtub of water, because it has so much more water, has more thermal energy. So we're going to calculate energy later on. We're going to have to take into account how much of that object do we have and what's its mass. In thermochemistry, we study the heat change in chemical reactions. Now, there's a couple of definitions that we want to get down. And one is the system and then the surroundings. So the system is the specific part of the universe that is of interest for us in a particular study. And here are some different systems here. So here we have what we call an open system. We have a bottle that has no top on it now, and there's water in here. And water can absorb heat or release heat depending on the surroundings. So there's a heat exchange in this direction here. And it's also because we have water in here, water vaporizes. We have water vapor escaping from the bottle and water vapor entering the bottle. So that's what we call an open system. Here we can have an exchange of both mass and energy. Now here we have what we call a closed system, and you can see why it's closed. We have a top on the bottle, so no more of that water vapor can escape. But we can have a heat exchange. So there is an exchange of energy here. And the last system that we have is what we call an isolated or adiabatic system. Adiabatic is a term we used to use all the time with these. I've noticed it's since dropped it out of the textbooks. But engineers still use that term, adiabatic. So in an isolated system, you want to think of this more like a thermal container. Here, it's closed, so nothing can escape from it, so there's no change of mass. But also because it's thermally lined, there's very little change of energy. So nothing really changes. So the system is that specific part of the universe that we're studying. Everything else is called the surroundings. So the point of these diagrams here is that our system is really what's in the bottles. That's our system. And the surroundings is everything outside of it. Now you notice we have a heat exchange between the system and the surroundings. Here we had a mass exchange between the system and the surroundings. Over here we had no exchange at all. Now in an exothermic process, we used this term before we discussed kinetics. An exothermic process, a system gives off heat. And if we would take the temperature of that process as it evolved, we would see the temperature go up. And we say that the system then is losing heat to the surroundings. Now here's an example. We have hydrogen and oxygen gases combining to make water vapor, and then the water vapor is condensing into water liquid. So we can see the water liquid here, and then we have energy released. Sometimes you can recognize an exothermic process if you have an equation like this, because energy will be written on the right-hand side of the equation as if it's a product. Here's another example. Now this is a physical reaction where you have water vapor, H2O gas, changing to water liquid. So this is condensation. So condensation always results in a production of energy. So energy is a product here. So exothermic processes can be both chemical and physical. Now an endothermic also can be both chemical and physical. In an endothermic process, the system absorbs heat from the surroundings. So the surroundings is losing heat to the system. Now we would notice that because it would appear to us that our system is getting colder. But what we are, when we measure that, we're really part of the surroundings. So we measure what's going on with the surroundings, and then we say what's happening to the system. So if I have a beaker in my hand and I add some substances to it, and it's an endothermic process in the beaker, that beaker will show a drop in temperature, and that drop in temperature will take heat from my hand, and I will feel cold. So I will say when something feels cold to me, that means an endothermic process is going on. I'm part of the surroundings, and I'm losing heat to the system. And I can't stop that unless I can put on gloves or something like that. But the process is still going to take heat from the surroundings because it can take it from the air. So here's an example here. We have some mercury 2 oxide, which would be a red powder. You may have seen this in a demonstration in a lab. If you heat this, you wind up separating the mercury from the oxygen. We can see them over here. And it makes what they call a mercury mirror. And the test tube would become, looks like very silvery, and that's actually the mercury vapor condensing on it. So this is an example of an endothermic process. Now, if I go back up to this one here, if you note, going to the right, producing energy was exothermic. Going to the left then must be endothermic. Again, we saw this in kinetics. So what would you call the process going from right to left? Well, if left to right is condensation, then right to left is evaporation. So evaporation of water is an endothermic process. And we notice that if our skin is wet and it's breezy out, we lose that water vapor quickly from our skin, and we notice that drop in temperature. You feel very cold. Now here's another example down here. There's a little friend from, looks like he's from a block of ice somewhere. So if we take H2O solid, which would be ice, and we warm it, and in other words, it absorbs energy, we make H2O liquid. So this represents the melting of ice. So the melting of ice is an endothermic process. Now the opposite would be the freezing of water. So the freezing of water is an exothermic process. Heat's released. Now, but we're part of the surroundings, and for us it happens when it's cold. We don't think of when water freezes that heat's released, but it is. Now, internal energy is what we're going to be studying today in this first part of thermochemistry. The symbol for internal energy is going to be capital U. Now, can we change the internal energy that something possesses? Earlier we saw the different types of energy that adds up to the total internal energy of a substance. We can change the internal energy by heating or cooling the system. But we're going to use a small q to represent the heating effect. Or we can also do work on the system or have the system do some work. And what we're going to see today is that work can be equated to heat, and heat can be equated to work. The total amount of energy that a system is going to either lose or gain is a sum of the heat effect and the work effect. Now here's a chart that gives us some idea what's going on then. So what we have down here, you notice, if work is done by the system on the surroundings, then the system is in a sense losing energy. It's using up some of its energy, and we're going to put a negative sign then in front of the work. If work is done on the system by the surroundings, then in a sense the system is gaining energy. That's going to be a plus sign then for work. Also, we can have heat absorbed by the system, endothermic process. You notice that's going to have a positive sign. And then an exothermic process will have a negative sign. Now here's the formula that we're going to be using. Delta U, change in internal energy, is equal to the heat effect plus the work effect. Now I do want to mention in some textbooks, instead of using a U, they would use an E, a capital E for energy, which is probably more apropos. All right, let's take a look and see about work. So here we have on the left, we have a system occupying a particular volume. This is its initial state, and it's under constant pressure. The pressure here is really just due to the air. It says the pressure of the surroundings. And then a reaction happens, and the system increases in volume. So the system must be doing some work in order to make the volume get larger. And so our formula is work equals minus P times the change in volume. Now the pressure is going to be constant. Change in volume we'd have to calculate. Now the negative sign is because the volume is increasing, and that means the system is doing work. If the arrow was the opposite direction, so that we went from a larger volume to a smaller volume, that means the surroundings would be doing the work, and the system would be increasing in energy, and then the sign would be positive. So a gas does work by increasing its volume. So you want to jot that down as well. So here's a problem where we can apply that formula to figure out the work that's done. Now we can equate work with heat, as I mentioned earlier. A joules is a unit of heat. So if we take a look at the question now, how much work in joules is done by a gas when it expands against a constant pressure of 1.2 atmospheres. Now we have a conversion factor that is going to link a change in volume and pressure to heat, and it's 101.3 joules equals a liter atmosphere. So this would be my P times delta V. So here's my initial system. The volume is 2 liters. The constant pressure pushing down on that volume is 1.2 atmospheres. So you notice that isn't changing. And my change in volume, my volume is increasing, and the change in volume is going to be the difference between these two. So that's going to be 4 liters. So here's my formula. If I plug in my values, I get negative 486 joules. Now you see how the units will all cancel. Now I'm going to get my pen. Like that one. Okay, so here's my pen here. So here's my atmospheres will cancel out. And my liters will cancel out. And that's why I get joules for an answer. Now that's actually a small amount of heat. Why is it a negative sign? Because the volume increased, and that means the system was doing some work. So the internal energy of the system has decreased by that many joules. Now here's another question that we can answer, similar to this previous one. A system absorbs 25 kilojoules of heat while doing 10 kilojoules of work on the surroundings. What's the change in internal energy of the system? So here we have to be careful of these signs. The system absorbs 25 kilojoules of heat. That means it's endothermic. That's going to be endothermic process. So we want to note that. So here's absorbs is key word, absorbs this much heat. And then it's doing this much work. So that means the system is going to increase by 25 kilojoules, and then it's going to decrease by 10 because it's doing some work. So here's our formula. We plug in our numbers, we wind up getting a difference of 15 kilojoules. So overall, the internal energy of the system has increased by 15 kilojoules. Now we're going to take a look at enthalpy and the first law of thermodynamics. The first law of thermodynamics is that energy can neither be created nor destroyed in a reaction. All it can be is transferred from reactants to products or systems to surroundings. So here's the formula that we had earlier. Delta U, or the change in internal energy, equals the heat effect plus the work effect. Now at constant pressure, which is the problems that we were just doing a moment ago, at constant pressure, the change in Q, heat effect, is equal to our change in enthalpy. Remember enthalpy we had back when we studied kinetics, which we're going to go over more today. Delta H, and work is equal to minus P times delta V. Now I can make a substitution in here. Since Q is equal to delta H, I can replace delta H with Q, or Q with delta H that is, and I have this equation now, which I can simplify to this. So if you notice, I'm going to be calculating delta H, and we're going to spend the rest of the chapter on delta H. And that why? Because delta H will incorporate both the internal energy change and any change due to work. And you can see that's what's happening here in our example. So we're going to spend the rest of the chapter now finding delta H. And we saw that in kinetics. You have to remember that the sign of delta H is positive for an endothermic reaction and negative for an exothermic reaction. So H is called enthalpy, and enthalpy is used to quantify the heat flow into and out of a system in a process that occurs at constant pressure. Most of the processes that we see anyway occur at constant pressure. In order to occur at constant volume, the reaction would have to happen in something we call a bomb calorimeter, where nothing can escape from it. So practically speaking, almost all the processes that we see at all always happen at constant pressure. So delta H can be calculated by finding the enthalpy of the products and subtracting from that the enthalpy of the reactants. So delta H equals heat given off or absorbed during reaction at constant pressure. So here's an example here where we saw this one earlier, water solid or ice becoming water liquid. Now heat is absorbed by the surroundings, and this is the value for it. So you notice that the units are kilojoules per mole. So for every mole of ice, which would be 18 grams of ice, 6.01 kilojoules must be absorbed just to convert the ice, which would be at 0 degrees, to water at 0 degrees. So the enthalpy of the products, which is the water liquid, is greater than the enthalpy of the reactants, and it's greater by this many kilojoules per mole. Now here's an example for a chemical reaction. Here our reactants are at the top. We have methane and oxygen gas, and we're burning the methane. We're getting a lot of heat released to the surroundings, and here are our products. You notice that the sign of delta H is negative, indicating an exothermic reaction. So this tells us that the enthalpy of the products, which would be the CO2 and the water, is a lot less than the enthalpy of the reactants. So we think of the methane and the oxygen as being high energy reactants, and the CO2 and the water as being low energy products. So here delta H would be less than 0 or a negative value. Okay. Now, thermochemical equations, as we just saw this in the last slide, is this reaction exo or endothermic? Because the system gives off heat, it's exothermic, and delta H would be negative because it's less than 0. Now this is one where we can read this. 890.4 kilojoules are released for every mole of methane that is combusted or burned at 25 degrees centigrade and 1 atmosphere. So you notice we have some conditions here you're talking about, temperature and pressure. These conditions are called standard state conditions. If the conditions were different, the amount of heat released may be different. So that's why you have to specify what's the temperature and the pressure. Now you don't have to worry about these changing because they won't in any problems that you might see. It's always going to be at this temperature and pressure. So here's our chemical equation. And you notice I can write delta H separated from the equation, and I put my value right here. Now, it says kilojoules. It doesn't say kilojoules per mole, but what it means is kilojoules per mole of methane, because there's only 1 mole of methane in the equation. But it would also be kilojoules for every 2 moles of oxygen, or this many kilojoules per 1 mole of CO2 produced, or this many kilojoules for every 2 moles of water produced. So we're going to have conversion factors that will link the kilojoules to the various numbers of moles from the equation. So here's my equation again with my delta H value. What is delta H? What is the change in enthalpy when 4.20 grams of methane are burned? Now remember that what we have now is a conversion factor between the heat produced and the number of moles of the substance in the equation. So it tells us that 1 mole of methane, because it's just a 1 here, 1 mole of methane is connected to 890.4 kilojoules produced. So our question involves grams of methane. So what we're going to do is convert grams to moles and then get our answer in kilojoules. So I take my 4.20 grams of methane, convert it to moles. I need to know its molar mass. So the molar mass is 1 mole to 16 grams. My enthalpy factor. Now sometimes in some books you might see them dropping out the negative sign when they pop it into an equation like this. And that's because there is no such thing as negative heat. There's only heat. Now the negative sign simply means it's going to the surroundings and not being absorbed by the system. So you notice our units that will cancel. We get an answer of minus 234 kilojoules. Now technically, if you go back up and look at the question, the answer really should be just 234 kilojoules. Again, the negative sign just saying it's being released. Here's an equation. I'm not sure about this page number anymore, but here's some sample equations with the delta H values. So you notice we have heat of neutralization. Here's an acid and a base, sodium hydroxide, hydrochloric acid. Exothermic reactions, going to be kind of hot now. How much heat? That will depend on, if this is per mole. If you didn't have, if you had weak solutions, you're not going to notice a big heat effect. You also have the heat of ionization, water liquid becoming ions. Isn't that funny? Same kind of number, but a different sign. We have the heat of fusion of ice. This means how much energy it takes to melt a mole of ice, 6.01 kilojoules per mole. heat of vaporization to vaporize a liquid. Now you notice it says it's this value at 25 degrees centigrade. At 100 degrees centigrade, the value is a little bit different because you are talking about breaking bonds when you talk about vaporizing the liquid, and those bonds are between the water molecules. Now you have many fewer bonds between the molecules the hotter the water is. So therefore it's going to take less energy to vaporize the liquid once you're up at that point. And the last one we have is magnesium chloride solid reacting with sodium liquid. This would be tough to do. Sodium liquid is tough to liquefy that, but can do the reaction, and we see we get an exothermic value. So why did the first two have opposite delta H's? Interesting. Well, if we write down the first equation like that, notice we can cancel out our spectator ions and wind up with the, looks like the reverse equation of this one. So this is really the chemical reaction down here. So what we notice is that the sign of the process will switch if the reaction reverses. That's something we're going to use later on.